Welcome back, everybody. We're going to pick up with bias variance trade-off. I want to discuss it a little bit. I want to discuss other loss functions as well. Recap what risk is, go through a couple examples. I want to tell you about something called phasing risk. It's a little bit different. Exam will be out today at 12 p.m., so I've written that up for you. There's 8 questions on it. I'm going to give you a week to do it. So you can come back and turn it in class on Wednesday in a week. Or you can email it. Both are fine. What I would like is you to write it up really neatly. If you write by hand or typeset. So a couple exams from last time I had a hard time reading through. If you do scan it in to me, and it looks like it's all bled out, and I can't read it, I can't read it. So, a couple of them strain my old eyes. So if you give me a little bit of a break, I always appreciate it. Of course, do your best, and I'll make do. 8 questions on the exam. I was going to put 10 on there, but I decided to give you a little bit of a break. Some of them are a bit challenging, and some things are directly from the book. So one thing I noticed from last time's midterm is there were questions in the book that some people still weren't able to do. And so that's a very good indicator to me that you don't read your books. So that's not all of you. I know some of you do. I know we try to do our best while we have a pile of work to do, but try to read your book. If you ever have free time at the beginning of a semester, start reading your book. So even flipping through it and knowing where things are in the book is a good idea. You might just be aware of where the particular example is that you're looking for. So there's a whole bunch of different levels that you read math books at. So it's pretty rare that you just go through it and read it word for word. But those paragraphs are pretty important. There are some book problems in here. I'll allude to one of them in my example. Okay, let's get on with it. So last time we wrote out the mean squared error, so the average of the squared differences. That's this thing right here. There's another name for this. So if we think about this function right here, the squared error is a loss function. Some people will call this the L2 loss. I use that language pretty often. So this is L2 loss. So squared error loss, you might call it. So squared error loss. Say one of these 2 things, most people know what you're talking about. Some people call it MSE. Some people approximate this by looking at actual samples in a simulation study. But this is an exact calculation. So keep in mind, this is going to be a function of theta. So function of theta. What it's telling you is, on average, how much you're going to lose for a particular value of theta. So if theta is some number, this equation expresses your average losses, where your losses are measured in terms of this function that you come up with. We've talked about L2 loss a little bit. One of the reasons we like it is because it's smooth, it's differentiable, and usually I can come up with an analytical solution. I can write it down on the board. I want to just point out, L1 loss, or absolute loss, two different names for the same thing. It's just this. My estimator, function of the data, minus the true absolute value. So this is my L1 loss function. If I take the expected value over this is going to be the risk function. So that's the L1 risk function. It's a function of theta as well. Usually we can't write down this solution analytically. So at least I can't do calculus to get this thing. So I want to point out that this always has something to do with the mean, and we've kind of seen that. So what we did when we played around with this is we shoved the mean in here. expectation EX. I added it in, I subtracted it, the expectation of my estimator, and I was able to expand everything and work out this form of everything. That it's a decomposition of the bias and the variance. So specifically, it's the bias squared, where the bias is just going to be whatever the expectation of my estimator is, minus theta. So that's just the difference between those two things. What I think on average and the truth. This right here will also be a function of bias and variance. Again, there's only two reasons you're ever wrong in something. Either because of the systematic error that you put into something, the bias, or the variability of your estimator, how much that estimator tends to bounce around. Some estimators tend to bounce around a lot. So hopefully they bounce around the truth, but if they don't bounce exactly around the truth, you want them to bounce close to the truth. And so those are the two things that we're thinking about. This is a nice decomposition, and you can just see analytically how this is a function of the bias and the variance. But in terms of all estimation, it has something to do with bias and variance. So I should probably say it has something to do with your systematic error and the stochasticity of your estimator. So it might not be the exact variance equation, but it has something to do with variability. So this right here usually has something to do with the median. And there's a good homework problem in the book that you can work through. I think it's either 7.13 or 7.14, and you can check that out in Excel Inverter. And I would say to work through that. So this is either 713 or 714, I just can't remember. And that solution is online in the solution manual, and I would say work through that and see how you work through and show how the median pops up. So optimizing over L2 loss usually has something to do with the mean. Optimizing over L1 loss has something to do with the median. I'll throw one more in. So if I just think about this loss function, some people call this L0 loss. This is just going to be this indicator function that if my estimator is equal to theta, so if this thing is a 1, this is going to be I should write it down like this, 1 minus this thing. So EX is equal to theta. This thing is equal to a 0. If my estimator is theta, then I score myself 0 loss, or I add in some arbitrary amount of loss. I could change this to a 5 or a 10, and it wouldn't change my solution. So this is EX. It's not equal to theta. So this is kind of your all or nothing criterion. This loss function has something to do, so the risk has something to do with the mode. Now, I'd say it has something to do with it depending on the context in which you're studying the problem. And so, if I'm dealing with empirical samples, then my something to do with something has to do with the median of the samples. If I'm working with L1 loss. If I'm working with L0 loss, then I end up looking at the modal quantity of the samples. If I'm doing a Bayesian analysis, then I'm going to switch the context that I'm working in if I'm dealing with L1 loss, my answer is going to be, my optimal answer if I'm working with L1 loss is going to be the Bayesian posterior median. Okay, so it's the median of the left. And this problem in Cassell-Inverter will help you to think through it. The mathematics involved in that problem are exactly the same, just depending on the context in which you're studying the problem. So I'll go into a little bit more detail as we run through this. But I just want to point out that these different loss assumptions are going to induce which estimator you want to use. What I've found in practice is statisticians are ill-equipped to answer which loss function you should be using. So it depends on the problem at hand. If you're just doing this arbitrarily, think harder about it. You know, think about why you're doing things. Usually I start thinking about things like, if I change my loss function, would I get a wildly different answer? And if the answer is yes, then maybe I should think about why I'm making the assumption. If, however, the loss function doesn't seem to matter, then maybe no big deal. So imagine I have normally distributed data, and everything was normally distributed. I'm in a classroom, so I can just assume things. In practice, we need to check. If you start ripping out outliers to make things look normally distributed, don't be surprised if you get clogged in the future. But if somebody deals with those outliers appropriately. If I were dealing with data that was normally distributed, and I wanted to build an estimator for mu, and I was working in the L2 sense, I would use the mean. If I were trying to build an estimator based off of L1 loss, I would use the median. And if I were going to use an estimator based off of L0 loss, I would use the mode. Now, if everything was normally distributed and n was really high, all of those values are exactly the same. So in a normal distribution, the mean is the median is the mode. So it wouldn't make any difference. Of course, with empirical samples, those might be a little bit off from each other, but if n went big, we'd all have the same estimator. So in a case like that, it doesn't matter. But if I were working with Cauchy data, and I said I wanted to look at the mean, I would have a real problem, because there is no mean. It would be all over the place. So there would be deviant values that are way off in the extremes. How do we deal with that? Usually we'll move over to the median, or something like that. The median's in the middle, it's well preserved. These outliers don't impact the medians. Okay, so if I take a value and I stretch it all the way to the right, I'm not going to change the quantiles of that distribution. So it kind of depends on what you're dealing with, but I just want you to think about this as a scientist every once in a while. Why do you make the choices that you make? If you go to a scientist and you say, well, my stats professor said it's not really a statistician's question, so you have to answer for me, what's your loss function? They're going to probably say something like, I don't know, I need my paper published. So if I don't get that, I don't get tenure in my whole life. So try not to think that way as you're developing your loss functions. Try to do it with scientific rationale. So if you explain things clearly, you'll get your papers published. So if you explain your assumptions, if you just make them fairly arbitrary, I won't be happy with you, but maybe your journal editor will accept it. So lots to think about in all of this. So I like to think about loss functions all the time. Saying that, I use L2 loss quite often. Okay, so in this right here, we can see the decomposition between the bias and the variance. This is not what is meant by the bias-variance trade-off. And I've seen a lot of books say this is what they call the bias-variance trade-off. And there's a fatal problem with that. Yeah, I can see that there's a trade-off in terms of the MSE, but they're presupposing that the MSE is constant, that this thing is constant, and that your contribution either came from here or here. So for a constant value over here, this can go up and that can go down, or this can go down and that can go up. It is possible to add bias to something and actually bring down the total level of MSE. And that's what the bias-variance trade-off is. And so you can add a little bit of bias to your estimates, and it might bring down the variance, but it might actually bring down the entirety of the MSE. And that's nice. And we want to be able to figure that out. We want to know if we can do that. And so we do have some theory for doing that, but I just want to run through some examples, because the theory sometimes doesn't push us in the right directions. It doesn't tell us what to derive in the first place. It just tells us what to check. And so sometimes we'll have answers, like we'll be able to say you can't do any better than this in a certain class of estimators, but you have to define that class in the first place. So I don't think that there's any general theory that says this is the best estimator without any restrictions. There is theory that says in restricted classes you can come up with best estimators. We'll go through this, through a number of examples. Let's look at one right now. This is in the book. So I'll leave some of the steps out and just fill in the details for you and have you look in your book. Let's just consider this example. You've been playing with this all along. We know all kinds of things about normal distribution. Xi is normally distributed. It's got some mean and some variance. So I goes from 1 to n. So we know a couple things. We know the expected value of x bar n. Just as a reminder, that's just the arithmetic average. This is equal to mu. That's unbiased. We also know, hopefully we know this, but if you don't know this, you can verify it. That the expected value of s squared, just as a reminder, this is going to be your sum of the squared deviations from x bar. So that's also unbiased. Right here, both of these are unbiased. In your Stat 101 conversations, usually they just ended there and said that's good reasons for picking these estimators. They're unbiased. Now, I would say if you didn't know anything about your problem, if you didn't know certain things about you in the process, it would be hard to argue with this answer. So this tends to be a very good answer under all kinds of different assumptions, and we'll have to go through those. It's unbiased. It also happens to be the minimal variance estimator in the class of unbiased estimators. So if I wanted an unbiased estimator, this in some sense is the best I can do, but I'm presupposing that I'm looking at MSE. I've got the L2 loss function. So very good under a set of assumptions. Now, of course, if I knew what mu was, I knew that maybe mu always has to be between 1 and 2. Then that would be a lot of extra information, and I could use that information to improve my estimator. So there is not reason to think that this estimator can't be beaten, but there's good reason to think that if I didn't know a whole bunch about the process, it would be hard to beat this estimator. It also is the case that the risk pertaining to this estimator under L2 is constant. That means for any mu value, my risk is always the same. And that's kind of nice. There's no boundaries in the problem, so I'm not pushing up against boundaries and changing the behavior of the estimator. And so it has uniform performance over all values of mu. It does not matter what mu is. If I use x bar, I'm going to perform the same over all different regions of mu. Of course, if I knew something about mu, I could improve that. And we'll say more about that in the next couple examples. This one is highly contentious. So this example, I just always hate this. I wish we could get rid of this and we didn't start off with the conversation that I like this estimator, I divide by n-1 because everything is unbiased and that's a good reason. I usually divide by n. So as we know that we know this thing right here, the mean, this is the MLE. It's also some sort of a mom estimator. So I could have derived it in two different ways. I probably could have made it some sort of a Bayesian estimator as well if I had some prior attached to it. So if I used the uniform prior on everything, which is the limit of the conjugate prior, I'd get back to X bar. So it might be a Bayes estimator, depending on how I derived it. But all this stuff that we're talking about doesn't presuppose how you derived everything. It's just checking how you evaluate everything. So you're going to have methods for deriving estimators, and then you're going to have methods that are universal in how you compare estimators. I'd say it's important how you derive estimators, but it's crucial how you compare them. So maybe I don't care how you came up with something, whether or not you say X bar is Bayesian, or if you say it's an MLE, or if you say it's long, maybe I don't care. So that'll have to do with you and your derivation, but I can check to see how well it works. Both of these are unbiased. I don't think that's a good enough criterion. We have to start checking the variance of everything. Now, I've already said that this has uniform variability for all values of mu. That means that this thing right here, the variance of X bar, this is sigma squared over n. This is a constant. It's a constant with respect to mu. So that means that the risk, if I think about this, it's unbiased, so the bias term is 0, and the variance is sigma squared over n for this example. So that means the risk function, this is going to be risk for X bar n, and I'm presupposing L2 loss. It looks just like this. This is sigma squared over n. And this is going to be over all values of mu. So it's constant, it never changes. I kind of like that. That no matter what the true answer was, I'm dealing with that problem the same way no matter what mu was. That's not true in the beta binomial example that we've seen. So as I get closer and closer to the endpoints, I have different performance out of my estimators. We'll talk about that example next. So we also know that this thing is not an MLE. So how would I have derived this? I tend to think of this as some sort of a mom estimate. So I'm taking a moment, expected value, of some function of the data. And then maybe I'm matching that thing. So I say S squared is about that thing right there. And you take it to be that thing. So maybe this is a mom estimator. It could be derived other ways as well. It could be some sort of a Bayesian estimator. I like to think about it that way because it'll tell me what my prior assumptions were. And then I can evaluate whether or not I like those assumptions. Lots to think about here. So basically, it's not enough to just think about the expected value of something, what its bias is. What we want to do is we want to think about what our losses are. And then we want to think about what the variance is, what the variance contribution is. I'm going to presuppose L2 loss to make my life easy right now. So under L2 loss, I could end up working out my variance. So I'll just write down the risk for S squared. So that's just going to be my expected value of S squared minus sigma squared. That's my truth. And I want to compare this in a squared error sense. So I can write down my bias for S squared, and I can add in my variance for S squared. We know what the bias is. It's 0. The variance, you might know what it is. Does anybody know what this is off the top of their head? I'm just curious. You could work it out. So how would you work it out? Well, you know what this whole thing right here, you can plug in this equation, sum of the xi's minus x bar squared over n minus 1. N minus 1 won't give you any trouble, so you'll deal with that appropriately. What you'd probably do is you'd probably expand all this out, and then you would know what the expectation of the xi squareds are. You could work out that second moment. I would probably presuppose I know what the variance is and then back calculate it all. I know what the means are, so I can compute all of that. But you could work all this out. Turns out it's this. 2 sigma 4 over n minus 1. And I would say it's a good practice exercise. Work that out. See if you can do it. But you know all the ingredients to work these things out. You can probably do it in less than 3 or 4 minutes if you're quick. Question is can we beat this? Is it beatable? Question. Can we beat s squared? And most of you know the answer is yes. You can definitely beat it. And I'll show you one such competitor. So consider the MLE. So the MLE is sum of the xi's minus x bar squared over n. And on the midterm, I ask you a lot of questions about these different functions, about what do you do with certain MLEs. So you get a lot of practice just from the midterm on this question. It's all stuff that's in your book as well. So the question is this a better estimator? It kind of is. I just want to point something out before we proceed in looking at this. Just a quick question. Question, is S biased? You said S squared is unbiased. What do you think?
Yes.
Yes. Yes. Why?
You can use it. You can show it using Jensen's inequality.
Jensen's inequality. Yeah, Jensen's inequality. So know that this is concave function. So we can use Jensen's inequality, and it's going to be strictly bounded by something because that's not a linear function. Hopefully that problem from a couple months ago helps you to think about it. So it is biased. So back in my Stat 101 days, I wish I knew this. I wish I knew what Jensen's inequality said, because quite often people are using sigma is equal to sum of the xi's minus x bar squared over n minus 1, and they take the square root over the top. So there's usually this conversation that goes, well, s squared is unbiased, and we estimate the standard error using this formula. It's biased. So there's a disconnect there. So that thing is biased. This is also biased in a slightly different way. So question is should we use biased estimators? Typically, if you transform something, you're going to be biased in something. So if you're not biased on one scale, you're biased on another scale. That's always true. So this whole thing of we don't want to be biased is a little bit elusive for me. You're always going to be biased somewhere. Maybe we like this estimator because it's the MLE. Maybe that's a good reason to investigate and check it out. On the homework, or on the midterm, I'm going to have you look at estimators of the form something like this. I think we know probably I want to multiply this statistic by some constant. I want to scale it somehow. And what they're going to do is they're going to work you through what the optimal estimator is of this form. What's going to surprise you is it's neither this and it's neither that. Shocking. There's other forms that you can use. Stuff that's in the book, as motivation, I cut this on the midterm so that you can work through that and read through your book. But it turns out there's other estimators of this form that this thing isn't 1 over n or 1 over n minus 1, it might be 1 over n minus 2. So that might be a better answer. much more sophisticated answers out there than just talking about the bias of something. So I'm not going to say this is the end-all be-all. There's still more to think about. But we can work through and look at the variance of that estimator. So I can work through and I can compute the variance of s squared, or I'll say variance of, I'll put a hat on there, variance of sigma hat MLE. This looks like a hard calculation. I'm just going to write this down as this is the variance of s squared, and I'm going to multiply by n minus 1, and I'm going to divide by n.
Do you mean the variance of sigma squared hat MLE?
Yes. Squared, right?
Yeah.
So I can just rewrite it in terms of s squared and recycle some results that maybe we know. So that would be the fast way through this problem. So this is going to be n minus 1 over n squared. Then I have the variance of s squared, and I've already written it down. 2 times sigma 4 over n minus 1. And I'll just let you guys know, you know how I remember this? I write it on my hand. So I wrote that on my hand this morning because I thought I would forget it. I don't actually know this off the top of my head, but I could write it in about 3 or 4 minutes. So those are the things I'm always asking myself. Could I prove it? Could I show them? So if you do that all the way through graduate school, if the answers become yes, and you can kind of mentally think through it, you'll be an excellent researcher and professor one of these days. So keep asking yourself those questions. Could I show this? If you're like, I'm not sure, take the 10 minutes and do it. Do it enough times, and they'll ingrain yourself with it. Okay, so we can work that out. We can also work out that the bias of sigma hat MLE squared, this is just going to be the bias of n minus 1 over n s squared. And we could work out what this thing is, how much bias there actually is in everything. So we could work out, if you want to, just work out the expectation first, and then work through the bias, the calculation. So this is just going to be expectation is n minus 1 over n. Expectation of s squared is sigma squared. So it's a little bit biased. I think this is a good, compelling thing to think about. I will say this. If you use n minus 2 over here, whatever you get when you optimize this, or you use n minus 1, or you use n and you say, geez, it really makes a big difference which one I use, I'm always going to say the same thing. You'll get more data. So if that's what you're quibbling about, you've got bigger problems. You just do not have enough data to estimate variance if this is making a big difference in your mind. Okay, but it's still a good mathematical problem. Okay, so we can work out what everything is. So the MSE, or I'll say the risk, for sigma hat squared MLE is going to be equal to this thing, n minus 1 over n squared. We could simplify a little bit. I'll leave it in unsimplified form. Probably should cancel one of those n minus 1s right there. But this is going to be plus n minus 1 over n minus, this is going to be sigma squared, minus sigma squared, that's the truth, and then I'm going to square that out. So this is the bias squared, and this is the variance. We could work out how this relates to the risk of s squared. And the risk of the s squared is going to be 0 bias. So this is going to be 0 squared plus this variance right here. 2 times sigma 4 over n minus 1. So that's my variance right there. And here's the big kicker in this problem. you're going to find out that is less than that. So it has less risk. That's always true. That's kind of nice. I kind of like this example. It says, if you bias something a little bit, you can lower the MSE. That's what the bias variance trade-off is all about. That's very nice. I'll let you analyze this and think about all the numbers and where all the ends are and simplify it. Probably draw a plot of this. See that they're probably pretty close to each other, but one is smaller. One is always smaller. So if this is true right here, that this thing always beats that, usually we say that the estimator that's always beaten by another estimator across all sigmas is inadmissible. So there's another estimator out there that can beat it. I'm not going to walk you through all those definitions, but it's an important thing. If you've got an estimator that can always beat you, you better hope it's not by much. So if you can always be beaten by some other estimator, why wouldn't you use it? So with that in mind, I have no idea why we use it. It is psychology. It's pathology. It is really weird. So saying that, if you continue to use it, I'm okay. It's no big deal. Slightly irrational, but not that much. So you're allowed. Okay. So anyway, biasing things can be a really good idea. I like that. So some people say Bayesians are always biased in some way. They're actually just prior. Good. You know, maybe that's a good thing. Let me just ask a question. Say, we assume some loss function. We assume some loss function. I'll call that loss L dx theta. You just make it arbitrary. And we have a point. Theta star that we're really concerned about. So I'll give this problem some context. I'll say xi's are normally distributed with mean theta and variance 1. I'll just take the variance out of the equation. I'm going to give you a whole bunch of data points. I goes from 1 to 10. So just some canonical example that we're used to thinking about. And I'm really concerned with what happens if theta star. And I want to bring my risk down. So question, how low can we make the risk at theta star? So let's just think about this theoretically. What's the theoretical lower limit for risk?
0.
0. So it's always something that's positive or 0, something non-negative. Can I make the risk 0 at theta star? Do you have any way of doing that? Could you construct an estimator that when theta is theta star, I'm always perfect?
Well, if you know what theta star is,
Yeah, if you tell me theta star.
then couldn't you just make it theta star?
Yeah, then I'm just going to pick theta star. So say theta star is 7 or something like that. 7. So I say, well, when theta is 7, I want to really protect my analysis. 7s are really important to me. Always try to protect my 7s, make sure that when the answer is 7, I get it right. Why? For whatever reason, I like 7 more than other numbers. So what you could do is you could take E of x and set it equal to 7. And it would make your risk 0 and 7. My point is that you can always bring your risk down at a certain point. What you want to be thinking about is the whole collection of thetas that you might be estimating. If you knew what you were estimating in the first place, then you just plug that right in. So a lot of people think about like global optimality. Can I be optimal over everything all the time and beat every analysis at every point? The answer is no. You cannot do that. So there's no like global concept of being optimal at every point in the set. What you can think about is being optimal across regions. So this example just helps us to think that. We can always bring down our analysis at some point. What does the risk function look like for this? So the risk for this estimator, and I'll just write down 7, EX7, just so that we know what we're talking about. My risk function for EX7, keep in mind I'm not using any data. I'm just saying, take your data, discard it, my estimator is 7. I'm really good at 7. So at 7, right here, my risk is 0. What does it end up doing? If I presuppose that this is L2 loss, then I know what this thing looks like right here. So this is just going to be my expected value of 7 minus theta squared. There's no data in there, so this is just 7 minus theta squared right here. That's just a parabola. So as I start to move away from 7, my risk starts going higher and higher and higher. So it's tempting to think that you can be perfectly optimal everywhere across a whole range, but you cannot. So you have to decide where you want to be good. Maybe you want uniform performance out of your estimator. Maybe you don't want it to get too high. So there's a lot of criterion that people think about. They sometimes think about minimizing the maximal risk. Now, I would say that's a very good idea if you're into building bridges or dams or something like that. So if you're a nuclear engineer, you're probably thinking about what's the most catastrophic thing that can happen. Let's guard against that. If you're going to the casino, maybe you're thinking about what's going to happen on average, and that would be a different criteria. So that brings up the concept of Bayesian risk. So Bayesian risk is average risk. So maybe instead of thinking about an interval and thinking about what its maximal risk is in the interval, maybe you want to deal with average risk. Again, this all depends on the application that you're dealing with. I wouldn't deal with average risk if I were building dams or nuclear plants. So on average, we should be fine. So we know how that works out. I do ask you a question about this on the midterm. But average risk, sometimes people call this Bayes risk, or integrated risk. I think if we phrase things like this, we wouldn't be so contentious. So I usually just think about average risk. So risk is an averaging over the data set in the first place. Bayes risk is going to take this one step farther. Bayes risk is just going to take your risk function. So risk, and I'll just write down, this is going to be a function of my estimator. I'll write it down like this because we've integrated out the data set specifically. And it's a function of theta. So what we're going to do is we're going to integrate this over theta. But I want us to just take a step back. Are we allowed to integrate parameters in our models? As soon as I integrate over a parameter in the model, I always think you're some class of statistician. I think you're a Bayesian. You're taking your parameters, upgrading them to random variables, and then doing something with them. This big fiducial divide back in the day. If you integrate over it, you're a Bayesian. And you'd better upgrade that to a random parameter in the first place. So I need a prior. If I don't want to sound as contentious or Bayesian, I might call this a weight. And what it represents is how much weight I'm placing on different values of theta. In this analysis, it's saying I'm placing all my weight at 1.7. We probably don't want to do that. We probably want to weight different regions. I think this is a totally reasonable thing to do, is look at the area under a risk curve and try to minimize it. But of course, it's going to depend on how I weight that space in the first place. So this thing right here is just going to be the integral of my loss function, EX, and theta. Then I'm going to have my sampling distribution, f of x, given theta. That's my data generating process, dx. Times pi theta, d theta. I probably want to say a few more things about this function. But oftentimes what a Bayesian is trying to do is they're integrating over this, and then they're going to do something with it. Maybe they're going to try to minimize it. So this is what formally a Bayes estimator is. So Bayes estimators. We've been kicking that definition around. The book even talks about Bayes estimators rather early before they actually present it. So this is what a Bayes estimator is. And I'm going to call this E pi x. That's my prior. I like to remind people that the way you weighted the space changes the answers. So if you had a different weighting to the space, you were going to come up with a slightly different answer. So this right here is going to be the arc minimizer over theta, integral loss function f of x given theta dx pi theta d theta. So I'm going to minimize the average risk. I think that's a reasonable thing to do. If you don't like placing weights, and you end up plugging pi theta is equal to 1 in all of that, I'm going to assume you've weighted your space uniformly. Maybe that's a good thing to do. So maybe that makes sense, depending on the context of the problem. This looks like a really hard problem to solve. So this is a variational calculus problem. It turns out it's way easier to solve than you think, and I'll go through this next time. But I'll just say this. Under L2 loss, the answer is going to be E pi x is going to be equal to the posterior mean. Under L1 loss, we're going to have that this thing is equal to the posterior median. And under L0 loss, there are other loss functions out there. This is going to be the posterior mode. And maybe I'll come back next time and show you that that's true. But that's kind of nice. So I take my posterior and I do something with it. And I grab an estimator. The full Bayesian answer is the posterior distribution. And maybe that's a little bit too much of an answer for some people. I want to give you your best guess. If you ever say, give me your best guess, and you're thinking about some optimality, you have presupposed an optimality criteria. You're going to have to explain that. So, but this gives us some mechanism for doing stuff. I kind of like these answers because they're conditional on the data, they follow the sufficiency principle. They might even be close to MLEs. Asymptotically, they probably are because the posterior is being driven by the likelihood function. And so asymptotically, they're going to peak so long as I have a reasonable prior and I don't put zero mass on the answer. they're going to converge into each other. So I kind of like all this stuff. Depending on how I form my prior, maybe I bias the problem in the right direction and I'm able to bring down variability, or maybe I mess everything up. Kind of depends on what theta is. So again, there's no global criterion for optimality, but there's at least some notions of optimality with some assumptions. I want to come back next time and I want to study the beta binomial problem. So I want to look at xi comes from, let's just say, a Bernoulli with parameter p. I goes from 1 to n. And I want to entertain a Bayesian answer to this, and I want to look at the MLE as well and show you differences between the two different types of estimators. So we'll pick up next time. There is a problem on your midterm that's going to pertain to this. And if it confuses you, it's in the book. So the answer to this problem is in the book. So read through it and I'll cover it next time. But I think it's important enough to dwell on a little bit, do some comparisons with you. So hopefully I don't have to grade that problem very hard. So we'll come back next time to pick up with that. Thanks, guys.